Hey everyone, this is Unit 4, Lesson 4, moving into systems of inequalities. Sticking with nonlinear systems for the most part, but doing kind of a combination of the two. Just a reminder that your inequalities are these symbols here where you have the less than, greater than, less than, equal to, greater than, equal to. Right. When you're graphing inequalities, graph your function as normal. So we have here the parent function of y equals x squared, which hopefully you know is this parabola. Okay, and the difference is you're going to do solid or dashed, right, and then shade above or below. So this one, the y is greater than or equal to, so I did a solid line, x squared. So since it's greater than, I shade above because all of these y values on this part of the axis are getting bigger. We're going toward y positive here. And so I want to shade above the line here. I know this over here is going up, but it's below our function. And so keep in mind that line is your function. So this one is your parent function. Y is less than that line, less than or equal to. So we shade everything underneath it. This one is above again, but this time it doesn't include the line. And so that's where we get our dashed lines. All right, it's not including that one there. And then same thing here. This one is a dashed line. And y is less than, so we can shade below. All right. So the solution to these inequalities is every point that satisfies the inequality, and that will be every point in the shaded region. So if you pick a point down here in the shaded region, so let's say that's -5, -4, something like that. If you plug that into this for y and x, then y will be less than x squared. So -4 is less than 25. That is true. So you can see it satisfies that inequality. All right. If we consider a system of inequalities, the solution to such a system is all points that satisfy all inequalities. So just like with our systems before, it has to make everything true. All right, so here's our first example. So we have x squared plus y squared is less than or equal to 4. This, remember, is a circle. So this is about recognizing your parent functions. So the center of that circle is 0, 0. And the radius is 2. Okay, so remember, circle equation is x minus h squared plus y minus k squared equals r squared. Okay. And then this is a line. Okay, color code these here. And the line, if we solve it, will be negative y is greater than negative x. So y is less than x. All right, remember when you divide by a negative, flip your sign. Okay. So I start by graphing. I'm going to start by graphing my circle. So I have a center at 0, 0 and a radius of 2. So remember, I go 2 this way, 2 up, 2 left, 2 down. And I connect those points. This is a solid circle. And so I'm going to connect them with a solid line. All right, and then this is a dashed line starting at 0, 0 and going up 1 over 1, up 1 over 1, or down 1, left 1, down 1, left 1. And so I can graph this line here. All right, so keeping in mind that we need to shade still. So the circle y is less than that line, even if we solve for y. Okay, sorry. And so we want all values that are less than a radius of 2. All right, so that's going to be inside the circle. And so I'm going to shade inside the circle here. Okay. And then for the other one, I'm not going to look here because my sign ended up flipping. So I'm going to look down here after I solved it. We want everything that has y less than that x. So y below that x goes down this way. So our actual solution region is where those shaded regions will overlap. So everything in this half of the circle is our actual solutions. And if you just want to shade that solution, then you can. All right, so if you want to look at where will that overlap be and just shade that. Okay. So it's just this region right here. Now we can still find where those 2 points, where there's 2 systems, where those 2 lines will intersect. And we can do that with either substitution or elimination. This one works well with substitution because y is essentially equal to x. And so we can say, okay, well, x squared plus y squared is less than 4. So x squared plus x squared is less than or equal to 4. So 2x squared is less than or equal to 4. So x squared is less than or equal to 2. So x, and I'm just going to say equals in this particular case, and I probably could have the whole way down, is positive or negative radical 2. If I plug that in, then I can solve for y. So positive radical 2 squared plus y squared is less than or equal to 4, and I'm just going to say equal to 4 here. So 2 plus y squared is 4, y squared is 2, and y is also plus or minus 2. You would get the same result with a negative 2 because when you square it, it would become positive. And we can see, square root 2. If we plug them into the second equation, that would work as well. If we have root 2 and root 2, if I subtract those, I get 0. And if we have negative root 2 with negative root 2, again, if I subtract something from itself, I will get 0. And so those are my 2 points. Now, because this is less than, those points are not actually included in my system. So right here, where those systems overlap, and I need to zoom in for this, you would actually have open circles. I knew that was going to do that. we would have an open circle at those points. And those points are not, I mean, you'd have to take the square root of 2 and then eyeball the decimal value here. So there's an open circle here and an open circle here. Just pretend it's open for me because it's hard to draw. But where those overlap, because one is dashed and one is solid, they would be open circles. Those points are not included in your solution set, but we can still find the vertices to this system. And later on, those will tell you quite a bit about a system. Okay. And so continuing that whole idea, we have a system here of linear equations. We just happen to have like 4 of them. It doesn't matter. Get them to where you can solve them. And so this would be, and you can walk through step by step, but this would be y is greater than negative 1/2 x plus 2. I subtracted x and then divided by 2. This would be y is less than x plus 1. Let me put these here a little bit. This one would be y is less than negative 1/3 x plus 3. And then this one would stay the same as x is less than 3, remembering that this is a vertical line. These are all dashed. So keeping that in mind when I graph it. So x, I'm going to go from the bottom here because x is less than 3 is this line here. I would shade this direction, and I'm not going to shade these. I'm just going to shade what's called my feasible region. And then we start at 3 and go down 1 over 3, down 1 over 3, down 1 over 3. Or we can go this way. And again, this is a dashed line. It is important that your graphs are accurate. And this one would be shaded below. So now we're this way and this way. We're right here. Because we're going to look at where these lines cross. So if they cross at whole number points, you can get those straight from your graph. If they don't, then you actually have to solve the system. But save yourself a little bit of work and try to use graph paper of some sort so that you can see where the lines are crossing each other. So graphing my red line here, this one has a slope of 1. And again, I'm less than this line, so now I'm in this section here. I'm keeping track of where my shading is going to be. This one is plus 2, and then down 1 over 2. And this one is above the line. So my shaded region is this little bitty trapezoid right here. Okay, so this shaded region is what we're going to call your feasible region. These lines will often be referred to as constraints when it comes to particularly application problems, because they'll be constraining your profit or looking at the different values you can or cannot produce for something. All right. Okay, so it looks like the only whole number for our vertice is this one here, which crosses at 3, 2. And that's where the green crosses the black. And so we don't really need to solve that one. However, we do need to solve where the red crosses the blue, the red crosses the green, and the blue crosses the black. The red crossing the black isn't important because it's not one of our vertices. Okay. So where blue crosses the black is probably the easiest one to solve because it's just substitution. So I'm going to switch this out for equals, -1/2, and I'm going to replace this with 3 plus 2, and I'm going to solve this out. So -3/2 plus 4/2, I get a common denominator there, 4 divided by 2 is 2, is just 1/2. So where the blue crosses the black, we have 3 1/2. Okay, so that's this point right here. Another vertice is where the blue crosses the red. And so again, I can just use substitution. So we have y is equal to -1/2 times x plus 1 plus 2. So -1/2 x minus 1/2. I substituted in the wrong spot. My Lanta. Let's try this again. X plus 1 is equal to -1/2 x plus 2. So again, that's 3/2 x, if I add that over, is equal to 1, multiplied by the reciprocal, so x equals 2/3. Sorry about that. So our answer here is 2/3, comma, and then to get y, you would plug back in to either of these equations. 2/3 plus 3/3 is 5/3. Okay. So that's where the red and the blue meet. So that's this point right here. So now I need where the red and the green meet. So same thing, I can just set them equal to each other. So I have -1/3 x plus 3 is equal to x plus 1. So 2 is equal to, this is a whole number, is 3/3 plus 1/3 is 4/3 x. So multiply this side by 3/4, cross divide, and x equals 3/2. Plug that back in, 3/2 plus 1, which is 2/2, is 5/2. So that point is at 3/2, 5/2. All right, and we already found that last vertice over here was, remember, at 3 and 2. So we have all 4 vertices for our feasible region. In what's called a linear programming problem, where you're looking for your maximum, you would have what's called then a profit function that you could plug these back into and figure out what the maximum value will be. We'll get to that later this week. For now, let's do one more video. It gets again longer than I want it to be. A coffee merchant sells 2 different coffee blends. The standard blend is 4 ounces of Arabica beans. I'm probably saying that wrong, but that's one type. And then we have Robusta beans, 12 ounces per package. Deluxe blends, and so we have a standard blend and a deluxe blend, uses 10 ounces, I should color code these, of those and 6 ounces of those. And the merchant has 80 pounds of those and 90 pounds of the Robusta. Find a system of inequalities that describes the possible number of standard and deluxe packages. So we want possible number of standard and deluxe the merchant can make. And so we have in the standard, four of the A plus 12 of the B. And then the deluxe, we have 10 A and 6B. And total, we have 80 A and 90 B. Actually, instead of mixing those so much, let's look at A and B. So we have and Robusta. Okay, in the standard blend, we have to have 4 ounces of these. In the deluxe blend, we need 10 ounces. We cannot exceed 80 pounds. Oh, all right, sorry, I needed to convert. So I take 80 times 16. That's how many ounces are in a pound. And then for our other type, we have 12 ounces in the standard, 6 ounces in the deluxe, 90 pounds total, so 90 times 16, so 1440. Because this is a maximum, that's where your inequality comes in. And so we have, we'll let x equal the amount in standard and y equal the amount in the deluxe. Because we want to know the possible number of standard and deluxe. So those are our variables. So we have 4x plus 10y needs to be less than 1280. And we have 12x plus 6y needs to be less than 1440. And so I will solve these real quick. I'm going to pause, solve these for y so that I can get them so that I can graph them. Okay, so I solved those for y, and I went ahead and made my graph. I counted by 8s. And so 128 would be here and 240 would be here. Just take those and divide them by 8. As long as your scale is the same on both the x and the y, you can still count rise over run as normal because the ratios will be the same. If I were to use different numbers down here than here, I wouldn't be able to do that. And so I'm going to go down 2 and then over 5 hash marks. It's about 5 right there. Right. And then I would continue that. This is a dotted all the way until it intersected over here somewhere. Okay. With word problems, you're just going to use quadrant 1. Sorry, lost my train of thought. And then I used the wrong color there to color code that, so you'll just have to forgive me. You would go down to over 5 every single time. My slope is also a little steep, so I'm gonna something like that. They're not going to be perfect, especially with that graph paper. I would hit somewhere over here. Okay. The other one, I need to start this whole video over again. That is the red one, so I should be going down 2 over 1, down 2 over 1, down 2 over 1. Every single time. I should have a pretty steep slope there. Okay. This one is going down 2 over 5. Down 2 over 5. Stop it. Here. Okay. Sorry about that. They're both less than, so this right here will be your feasible region where it's less than both lines. Okay? Sorry about that. Okay, and that video is way longer than I meant it to be. Sorry about the fumbles. Hopefully the sound quality is good, and have a good day.